Thanks for the introduction from David. So this is Haohuan. I'm from Tsinghua University and also the National Supercomputing Center in Wuxi. First, I'd like to express my thanks for the invitation to this very interesting workshop. And also, as I was talking to Jianping, is actually I think my first academic talk of this year. And actually, some of my friends just sent me a very interesting message. So today is the day of 21 in the year of 21 in the century of the 21. So a very special day for an interesting workshop to start. So my topic is actually some of our existing efforts in the last, say, 5 years for making climate modeling more efficiently and more scalable on our supercomputer Sunway TaihuLight in our center. And also I'd like to report our very recent efforts with climate scientists to actually generate some interesting data sets that people can start looking at. Okay, so first, still, I think I still would like to use just the one slide to point out some of the major features of the Sunway TaihuLight supercomputer. It's a many-core processor that we're using. Each processor has 260 cores. And it's actually, as you can see from the figure, it's actually divided into 4 core groups. So each core group has one, we call it management core, which can do both computing and all the management task. And then there's this 64 computing cores organized as a 8x8 core array. That's the major computing force of this machine. It used to be the fastest supercomputer in the world and providing a peak performance of 125 petaflops with over 10 million cores. So actually, you can see this one is very, architecturally is very different from the previous machines that we have in China, which also means that we have a lot of challenge to make application softwares efficient on this new supercomputer with new architectures. So that's what we call the application challenge, because so I think on the top 500 list, this supercomputer is still the fastest supercomputer in China. And of course, we want to use it to support some of the cutting edge science and engineering research efforts in different institutes in the country. Now, what we need, of course, is this application software in the middle. And especially for myself, I'm also working as a professor in the Department of Earth System Science in Tsinghua University. So a lot of our focus is actually for earth science related problems. So this figure is actually, I borrowed this figure from the very famous Earth simulator in Japan. I think this figure shows a very clear picture of what we want to do using supercomputers for geoscience problems. So basically, as computer science people, we want to create a digital Earth so that we can simulate different kinds of phenomenon that happens on the Earth, and then we can analyze all the different changes, and then we try to understand what is the underlying mechanism of all these different change, and so that we can try to make predictions into the future and provide guidance to politicians about how we should mitigate this change. So actually, I think climate is actually one of the most traditional application domain for HPC supercomputers. If you look at the history, I think the very first computer, ENIAC, we already have the efforts about numerical weather simulation. And of course, NCAR, the National Center for Atmospheric Research, they pretty much have all these different generations of supercomputers. And they have the very first Cray one, which is usually considered as one of the most successful supercomputers in history. And also, of course, the Earth simulator I've just mentioned. Now, what we see in this transition, this is a figure I borrowed from the NCAR website. If you see the change of architectures along the year, right, from the Cray vector machines in the beginning, and then to the clusters with different kinds of cores, and then from IBM cores to Intel cores, and most recently we're starting to see climate people and weather people are starting to use GPUs and other heterogeneous architectures. And these changes of architectures that bring a lot of challenges, especially for application software developers. So that's actually kind of the challenge we are facing when we first try to start our climate modeling efforts on the Sunway TaihuLight supercomputer. So this is a very brief summary figure about all these efforts we did in the, say, last 5 years, trying to make climate modeling sort of efficient and kind of usable for climate scientists on this new supercomputer. So in this slide, I show some of the sort of major challenges I see in this process. Of course, I think some scientific codes in other domains also share the same challenges when we switch from one architecture to another architecture. The first one is, of course, the complexity of the code. So usually these community scientific code are developed by many different groups all over the world, and through usually through a long period of time. So it has a high complexity in the programs, and also heavy legacy in the code base. Some of the programs that people are using might be written like, say, 10 or 20 years ago. So it's a very complex code that you need to, say, port to a new architecture. And then if you look at the code, usually it's multiple MPI programs that you need to couple together. And obviously, most of the kernels, most of the compute intensive parts are designed and optimized for the previous architectures, not for the new ones that you want to be using. So there's this misfit between the design philosophy and the new hardware architecture you want to port this code to. And also, if you really want to, squeeze all the computing power of a supercomputer and try to compute something really complex, it will be a systematic effort that involves all the different parts of the machine. Usually you need to run the simulation for a long period of time. It will generate very large volumes of data sets, and usually it involves very complex communication because of the scale that you want to do this kind of computing. So you need to pretty much consider all these different problems along the way that you try to make your program sort of more efficient. And especially in our part, we see the biggest challenge is, of course, the lack of people with interdisciplinary background. So in our case, when we started the project, we have very strong background in computer science, but not so strong background in climate or in weather. And that turns out to be a very big challenge along our efforts in the last 5 years. So this is where we started in the year of 2015. It's actually maybe half a year before the machine was ready. So we were trying to see if we can actually, make use of this common machine and trying to do some climate modeling experiments for our department. So at that time, we set up this team. So this is actually a photo of me many years ago, not say at the time of the project. Anyway, so we had gathered a group of people, like maybe 20 or 30 people from both computer science and climate, but maybe only one professor is from the background of climate modeling. And then we have most of the students coming from a computer science background. So as the hardware engineers were building the Sunway TaihuLight machine, we were trying to port the CESM. So if you are working in the climate domain, you should be very familiar with this CESM Earth system model. Is probably one of the most widely used climate modeling program in the world, with the atmospheric component, the ocean component, the land component, the sea ice component, and also of course the coupler to connect all these different components. So we had a very intensive project, a 3-month project, trying to port over 1 million lines of code onto this very new supercomputer and trying to make it run. So when I look back at the project, I was surprised that we actually managed to accomplish our primary goal, that is trying to make it run, okay, and then trying to make it run not so slow on this new architecture. So we did it actually in the 3 months. We can actually scale to I say pretty reasonable scale with 24,000 MPI processors over 1 million cores, and we even get some speed up for some of the computing cores, pretty good speed up. Well, but the bad part, as I said, most of the students, they are from the computer science background, and throughout the project, the biggest challenge is that they don't, they read the code, but they don't really understand what's the philosophy behind the code. And that actually makes the porting part, the debugging part, very challenging. And I should use the word very intimidating for the young students. So, a lot of them chose to drop out of the project after the 3 months efforts, because it's really very challenging work if you don't have a very good climate background to come along the way. So this is the year of 2016. So I think in this stage, we only have in the authors, we put all the members that have contributed to the project. But by the time that we actually send the paper to supercomputing, we only have four or five students of them that are still willing to continue working on the project. And this is, I should say, the first stage of the project that we try to refactor the code onto this new machine. And as you can see from this figure, if you want to know some more details, you can try to refer to our supercomputing paper in 2016. So basically, we divide the, and most of the efforts are sort of, the performance improvement efforts are focused on the atmospheric component, the CAM part. So we basically divide the CAM into the dynamic part, which is actually relatively newly organized code. So we can actually look at the code and try to do some manual transformation of the code to make it suitable for the new many-core architecture of Sunway. For the physics part, is very, as I mentioned, it's very challenging to actually read and understand the code. So for this part, we try to rely on the code transformation tools. So we're using the ROSE framework, and we write some tools to actually transform the loops. So the key goal is actually trying to look for the most suitable level of both parallelism in computing and the size of intermediate variables that we need to store in the memory, especially in the fast memory. So trying to find the most suitable balancing point for the loops to be loaded into these different cores. So this is the first stage. We most of the efforts are refactoring efforts, and this is the sort of the results we can get for CAM 25 kilometers by using say 24,000 MPI processes. We can get a simulation speed of 2.8 simulated years per day. So in the year of 2017, with the people that still are willing to work on the code, we take an even more aggressive approach towards the code. We try to actually redesign a lot of the parts of CAM-SE, trying to make it more suitable for Sunway TaihuLight. So when I say we want to make it we redesign it to make it more suitable, that means we are going to change the way that we store the data elements in the loop. And we are also changing some of the internal threading parts, trying to make it sort of more suitable to the code. And that relates to the switching of the programming philosophy also. So on Sunway, on the many-core architecture of Sunway is kind of similar to the NVIDIA GPUs. We provide two levels of programming interface. The first one is OpenACC. So it's similar to the OpenACC in CUDA, but we have made some customization to support some of the special hardware features, such as the register communication along the 8x8 core arrays and sort of other features. So that's the first level. The second level is what we call a thread. So that's basically you write your own threading code to control all the different parts, especially the memory control. You can do a much finer memory control of all the data elements, and you can also do more efficient vectorization. And also the register communication feature is also can only be achieved by using the a thread programming interface. So that's the second stage. We are actually trying to do some of the dirty work, trying to rewrite a lot of these different kernels, and that's actually where we start to see the good performance improvements. So if you look at these three bars, the first one is the starting point is the porting. Is the ported code. So we just port the code onto the management core of the Sunway processor. And you can see as the Sunway core is much simpler than the Intel cores. The performance is only 1/10 or 1/3 of what you would achieve on an Intel core. And then the second bar is after the OpenACC based refactoring. And we start to see some performance improvement, but not so impressive if you think about that. We're actually using 64 computing cores to do the computation. And then only after you actually redesign all these different parts, how you organize the data elements, how you do the threading of these different things, how you do vectorization, and then you start to see some good speed up numbers. And that's where your performance really starts to show some potential on this new architecture. So this is the work we have done in the second stage. So of the 750,000 lines of code, we have modified 1,050,000 of that and added another around 60,000 lines of code. And for all the different kernels, we have pretty much covered 80% of the total runtime to make it sort of more suitable and more efficient on the Sunway architecture. So this is the simulation results we get in the second stage. We were able to correctly capture some of the major features of the Katrina hurricane using the this redesigned program. I think this might be some very simple practice for people working in climate or weather field for many years. But for us, is a very exciting starting point, because we start to fear that the program on this supercomputer will be growth into a stage that can really get scientists to use it to produce good results. So based on that, actually, in the summer of 2018, we had, you can see from the name of the authors, is pretty much all the climate-related professors in our department and many of the students that spent the summer in the Supercomputer Center in Wuxi trying to make our model is a Earth system model developed by our department in Tsinghua University. We call it CESM, trying to make it run on the Sunway TaihuLight supercomputer. And we have also, they have used Sunway TaihuLight as the platform to accomplish all the experiments of CMIP6. And also, it's also from the year of 2018, we start to collaborate with the climate scientists in Qingdao. There's a National Lab for Ocean Science and Technology in Qingdao. So the researchers there and also researchers from NCAR, we start to collaborate to trying to really optimize the high resolution community Earth system model. We call it CESM-HR on the Sunway TaihuLight platform. And this is the work we did along the way from the October of 2018. I think till now we are still working on this CSM model, and you can see we repeat. Unfortunately, we have to repeat some of the efforts we did before because there's a major version upgrade of the CAM, especially the CAM model. There is a lot of upgrades in the program, so we have to repeat some of the refactoring and redesigning efforts. And then after that, we did some even sort of more related to the system functions. We have to, according to the features of this very large scale. So in the production run, we have to use, say, somewhere between 50,000 to 60,000 MPI processes to do this high resolution CSM run. So we have to even customize the malloc functions, the MPI functions, and we have to customize the load balancing strategies to get even better performance in this case. So actually, so the performance results is where we get, I think, in the year of 2019. So now, for the entire model, we can achieve a speed that's very close to 5 simulated years per day. So I think that's a good starting point that scientists would like to start using this to do much century simulation. So this is the experiments we have accomplished. I think from the year of 2019 to 2020. I think we have, as I mentioned, we have used up to 50 or 60,000 MPI processes. That's roughly 1/3 of the machine to do this kind of high resolution run. And we have completed 500 years of pre-industrial simulation and also 250-year historical and future climate transit simulation with the CAM resolution at 25 kilometers and the POP, the ocean model resolution at 10 kilometers. So here is just some visualization results of the simulation we have accomplished. So as I said, I'm actually not from the climate science background, so I might not be the best person to talk about the results. I'm just going to show you some of the highlight figures. So this is the global mean surface temperature. So as you can see, here we shows the sea surface temperature and also the temperature at 2 meters. As you can see, the high resolution obviously it shows a better consistency when you compare it with the different kinds of reanalysis data sets. It shows that it's kind of more consistent with the observations. And the other thing we are very interested, especially for high resolution simulation results, is of course the tropical cyclones. You know, how well you can capture the hurricanes, the typhoons. So here is the results. As you can see, the first figure is the results of the observation. And the second one is the high resolution results. The third one is low resolution. If you compare with the low resolution, so the low resolution is very clearly underestimated results of the number of tropical cyclones. Now for the high resolution is kind of closer. We say the TC numbers are kind of corrected to some extent, but of course, in this case, is kind of overestimated a little bit. But if you look at the patterns, it's actually also coming closer to kind of to the observations. So if you are interested about this data set, I think this paper is already online now, so you can get some more details about these results. And actually, it's huge volumes of data sets. We are also working with our group of climate scientists trying to develop some more efficient and more intelligent tools so that people can really look into these data sets in a more efficient way. Okay. This is my last slide, a very important slide. So we are also looking for postdoc researchers. So if any of you have, freshly graduated PhD students, if they would want to have an opportunity to work on these Sunway supercomputer machines, please forward them this information to them. We are looking at people to work on both HPC applications and also, of course, big data for science. As I mentioned, for the huge volumes of data we have generated, we should be looking at different kinds of analysis methods that we can be using, and also the software tools, both for porting the code, transforming the code, and also for scheduling these very complex workflows that we're looking at these days. Okay, so with that, I should end my talk, and thank you for your attention.